Let's talk about the shear modulus, also known as the modulus of rigidity. If flashback to Young's modulus, also known as the modulus of elasticity, shear modulus, modulus of rigidity. And so if I have a surface here, I think a good way of picturing it is picture that the bottom surface is fixed, and so not going to move, and you apply a force across this top area that is parallel to that surface. Then the shearing stress, which is normally force divided by area, is that force divided by that area on top. It's not the area on the side, it's the area on top. Shearing strain deals with the fact that I have this material that is going to get distorted, and shearing strain is equal to that angle right there. Now, if that angle is small, and so you might want to look back on some of the other videos dealing with radians, but this is what I'm getting towards is a small angle approximation. So if phi is much less than 1, this is symbol for much less than, and notice there are no units here, so I'm talking about radians, then we can use the small angle approximation, and the small angle approximation says that phi is approximately equal to sine of phi, which is approximately equal to tangent of phi, which is just going to be, well, tangent of phi is the opposite over the adjacent, so d over L. And so when we're talking about trying to calculate the shear modulus, we have our basic formula here, which then translates into that. And if the small angle approximation is applicable, then we can take it the next steps and ultimately end up with this. Do want to point out that some sources, instead of using the S for shear modulus, will use the Greek letter eta, like an N with a big trunk up front. And a quick note that I'm not using a sub 0 since the area here is not really changing. All we're doing is just pushing it off to the side, displacing that top area. So if we go into a little bit more specifics here, do some of the math. So we start out with A, B, C, D as the side, and then I apply this force to the top, and I shift it the top distance D. So originally I have it like this, and it gets skewed, but if I look at it from this point of view, so looking at that triangle there, in essence, there seems to be pulling it in that direction and pushing it in that direction. And so we're going to basically look at it from a slightly different viewpoint here. If it started out as a square, then this force being applied, we can treat as so equally pulling on it as it is pushing on it. So this shear force causes a longitudinal stress and a transverse stress. And we can assume that those two stresses are the same because there's no reason why that force would cause favor to one direction or the other. And this is basically saying the same type thing. Actually. Now, if I'm pulling on here, let's ignore this force for just a moment. If I'm pulling on here in that direction, this is naturally going to come in. And so this longitudinal stress is going to cause a transverse stress in that direction. Likewise, if I ignore these forces and look at just the force that's pushing in like this, this would now be called a longitudinal stress. And it's going to cause a transverse stress in that direction. Longitudinal being the direction the forces are applied, transverse being perpendicular to that. And so I have two things involved here, which I will now bring down to here. So I know that the longitudinal strain is the change in length in this direction from whatever the diagonal is length there to this length over the initial length. So the measure of AC prime minus the measure of AC, so that's the change in length over the measure of AC, which was the initial length. So that would be the total. That's got to be equal to the longitudinal strain from the longitudinal pull, as well as it's got to be from the transverse strain from the transverse push. So remember, these are causing that to bulge out as well. And since alpha is strain divided by stress, which is 1 over Young's modulus, and beta is strain over stress in the transverse direction, then this longitudinal strain is just alpha sigma sub L and beta sigma sub T. Since we are claiming that the stresses are the same, alpha plus beta come out, and so we got alpha plus beta times sigma. So our total change in length is got to be, well, that is equal to this. So I multiply both sides by L sub O, and so I have my change in length here is alpha plus beta sigma L sub naught. And L sub naught is the initial length across here. And basically I've got, if I look at it as a triangle, I've got L and L. And so this length right here is just L square root of 2. So down here, my initial length of that diagonal is L times square root of 2. I'm now going to look at how much it's stretched in a slightly different manner. So if AE is equal to AC, so this distance from here to here is how much it has stretched. Now this angle here is practically a 90-degree angle. We are assuming not a lot of deformation here. And therefore, this angle right here is roughly a 45-degree angle. And so therefore, the measure of EC prime, so this distance right here, is the measure of the hypotenuse times the cosine of 45 degrees, or sine of 45 degrees, whichever way you're feeling at the moment. And cosine of 45 degrees is square root of 2 over 2. And the measure of CC prime, the hypotenuse here, is just D. And so that is another way of finding the change in length off the original. And so now I set what I did on the other page to what I have here. And if I work through the math, I end up with sigma over phi, which is the definition of the shear modulus. And that's going to be equal to, well, 1 over 2 times alpha plus beta. Now, why we need this at this point is not necessarily obvious, but it is going to come into play into another video.